All right. Good. Finally, after 12 minutes or so, we can start. So, to recap a little bit what we did last time. Last time I introduced the concept of an S matrix and of differential cross-section. So, the S matrix, as we saw, was something that related, the probability amplitude to go from some initial state to some final state, and as an operator was related to E minus Hamiltonian times 2 times the time, in the case where the Hamiltonian is time independent, of course. And then we divided it into a piece which is 1, meaning that there's no interaction, and the remaining piece is called IT. And then the matrix element between states with momenta, let's say 2-particle state initially and n-particle state finally, is 2 pi to the 4th delta function of momenta times I times the amplitude m. And then we have seen that these S matrices, or more generally, the S matrices with the inclusion of some operator A of 0, so without A of 0 would be the simple S matrix from before, were related to the momentum space n plus m point function, so correlation function, via obtaining the residue at the pole where the momenta are on shell. So I multiply with this factor that goes to 0, d squared plus m squared minus I epsilon, and then also I consider these loop factors, which, as I said, come from the fact that the 2-point function, so G2 goes like I z over d squared plus m squared minus I epsilon. So in this way we relate the S matrix elements to the things that we have studied before, the correlation function. But the S matrix elements themselves, specifically this object defined here, M, was related to the thing that we experimentally measure, the differential cross-section, via a formula that we derived, which is modulus m squared over 64 pi squared center of mass energy squared. All right. So today we're going to write Feynman diagrams for the S matrix. So we've seen that the S matrix is the one that's related to physical observations, and now for it we will derive perturbation theory and Feynman diagrams. So first, let's start with this perturbation theory for S matrices, an analog of the Feynman theorem and the Fick theorem. All right. So the first observation is that when we wrote S matrices as the matrices of this, so P1, P2, E minus I, H, 2T, Ka, Kb. So we define in and out states, which are Heisenberg states, and then in terms of the Schrödinger states, these were evolved in time in the Hamiltonian. But in both ways of thinking about things, these states were states in the full theory. So states that are obtained by acting with some A dagger on the full vacuum omega, right? So, but we've seen when we define perturbation theory for the Green's functions that the way to define the perturbation theory is to define first states of the free Hamiltonian, H0, and then in them we find perturbation theory in terms of the interaction picture. So before we had introduced a relation between the vacuum of the full theory for H and the vacuum of the of H0 only, as a limit when time goes to infinity 1 minus I epsilon of, well, the state propagated with H0, and then the transition amplitude for the two vacua. Okay, so we take, so this is the vacuum of H0, and we propagate it with a full Hamiltonian, and then divide by this normalization factor, which is, I mean, E0 acting on E0 is the Hamiltonian when acting on omega 0, on omega. Sorry. Okay. And then further, this exponential of the Hamiltonian is the evolution operator. So, well, let's write the same thing. And then here, this is the evolution operator in the interaction picture between time minus t and 0, acting on 0. And the relation was found by the completeness relation, for the Hamiltonian. So these are eigenstates of H. So the eigenstates of H form a complete state of a Hilbert space, and then the vacuum is the state that has energy E0, which is minimum. And then this prescription was introduced since if I multiply in here, I get minus I times minus I is minus 1. So minus epsilon times something, times t in particular, which goes to minus infinity, which goes to plus infinity, excuse me. So this whole exponential will go to 0, leaving the only contribution, the contribution of the state with energy 0, that is the vacuum. Right, so in this way, we are able to make a relation between the vacuum of the full theory and the vacuum of the free theory. However, right now, we want to do something similar in the case where we don't have a vacuum anymore. So now, the relevant case is where we have some, well, let's say in here, Ka, Kb. So we have a state with two particles or some number of particles acting on the vacuum. So now, we want similarly to relate this state with the particles in it with the same limit t going to infinity with 1 minus I epsilon e minus I ht on, and now we cannot say the free vacuum, but rather the similar state with two particles of the same momenta in the free theory. So Ka, Kb in the free theory, 0. And unlike in here, we write a proportionality constant simply because the actual normalization is a little bit more complicated. Now, I mean, because since we have an external state that's not a vacuum anymore, things that will be involved will be loop corrections and so on. So the normalization constant is a little bit more complicated, but as we will see, as always, the normalization constant is irrelevant since it will cancel out in physical calculations.
Is it possible to show that, or you are assuming that both is in the relation?
No, I mean, the logic is exactly the same. So it's just that the exact equality involved us having this particular normalization constant involved us taking a scalar product and defining a two-point function, right? And then because it was both states were vacuum, one of the full theory, one of the other of the free theory, it involved only this exponential. But now it will involve things that are a bit more complicated. So the normalization constant is a bit more complicated, but the logic is still the same. We still introduce this identity, introduce it in here, right? And then the same thing happens because of this limit that we keep. We'll get the same E minus epsilon t times the energy, which again keeps just the vacuum state, right? So, and then when we act with KAKB, this is still, because in here in principle we still have KAKB, which are some A daggers, but acting on a vacuum state. Otherwise, in here they would act on a state n, energy n. But because of this limit, only the contribution to the vacuum state is relevant. So the proof is really exactly the same as far as this part is concerned. The only thing that's different is when we take the scalar product of two of these things to find out the normalization constant. All right. So, then we want to redefine this object, right? So this is the quantity that is our S matrix. And now we want to rewrite it using the formula above. So we want, well, let's call this 1, say the right hand side of 1 is limit when t goes to infinity 1 minus I epsilon. And now we write these momentum states in the free theory. So putting a 0 in here. 2. And so let's say E minus I H times 2t. And sorry. Yeah, that's the point. It's proportional to EAB, say 0. Okay. So nothing has changed. So there's the proportionality constant. Then there's this factor in here. But of course, when we take the dagger, I have another factor is a plus, which cancels this because in the midline I have the same Hamiltonian. And then the same relation that we proved before. So this was still related to the, so this was this exponent of the full Hamiltonian E minus I H2T was equal to the interaction, the evolution operator between minus T and 0 in the interaction picture. Well, sorry, E minus IH is minus T and 0, E minus 2 IH is between minus T and T. And sorry, let's say UI minus T. And then, as before, you remember we've written a differential equation for the interaction picture evolution operator, which we then solved in terms of the interaction picture Hamiltonian, and in terms of the because we want now to, we have a kind of bizarre object at this point, right? We have this object that is an eigenstate of H0, but here we have H, right? So the reason is that what we want to do is we want to rewrite everything in terms of the interaction picture. So in the interaction picture, this object is still a state, right? So this would be a state in the interaction picture, but the object in here is the evolution in the interaction picture, which must be written in terms of the Hamiltonian interaction picture. So this was written as before. I mean, this is the same proof, it's the same object as the time evolution, time ordered product of the exponent minus I integral minus dt prime h I. And yeah, here, what they will call this PA PB 0. Okay. And so this is some final state. This is the evolution operator. Well, in this limit, understood as evolution operator from minus infinity to plus infinity in the interaction picture, and then some initial state. All right, and as I said, the proportionality means there's some constant in here, but as before, we will be using the Feynman and Wick theorem. And if you remember there, what the result was that we had a ratio of two objects of this type, so any constant imprint that appeared in one would cancel against the other. Okay. All right. So here similar things happen, although again the proof of the theorem is a little bit more involved because the actual proof needed an equality in here. So I will not be showing the proof in this case, but it goes on similarly. So in the end, the result of this is that the amplitude that we're looking for, this one, P1, P2, so on IT, PA, PB, so result of all of this is as I said, there were these factors of square root of z. So these are part of the issue that we're describing, the issue with normalization constant. Then we have this limit for time, and the free states, this time order product, and PA will be 0. And the final thing is also part of the issue of proportionality in here. The corresponding result must be what is known as connected and amputated. So from now on, I will describe what that means, and I will try to derive it using examples. All right. So one observation is, well, I considered here IT instead of S, which was what we had in here was S, right? But the point is, first of all, shouldn't connect these things to begin with, because we're looking only at interactions. But second, this is related to this issue that we're going to describe now of what it means to be connected and amputated. So the connected and amputated part only relates to the interaction picture, IT, dropping the S. So the relation is on this side you drop the 1, and on this side there's also the part of the proportionality constant. Part of it is this, and the other part is the connected and which also has to do with dropping the 1. All right. So now, and one more observation. These factors at tree level, without quantum corrections, don't exist. So this is only something to do with loops. So, to understand what's going on, let's look at examples. So, the simplest thing we can think of is a 5-4 scalar theory, and we'll consider it in first order perturbation theory first. Then we'll move on to higher orders. But well, first let's consider the free term. The free term on this side. So if I look in here, I have time order exponential of something. So the free term, the zeroth order term, is just when I have the product of the two states, right? So the free term, zeroth order, on the right hand side is, well, for it to be non-zero, I have to have the same number of particles in the final stage, right? So n equal to 2. So let's say P1, P2, and P8, Pb. Okay? And this momenta state means a dagger on the vacuum with a relativistic normalization, which was square root of 2 energy. So this is square root of 2EA, 2EB, 2E1, 2E2 from the normalization, and then 0, A1, A2, and A dagger A, A dagger B, 0. Okay? And then the product well, you remember there were two ways to do it. I mean, either saying that this is the norm of A dagger 0, or just commuting this past. So A dagger is 2 pi cubed times square root 2e delta 3 of momenta, right? 2EA, 2EB. Anyway, sorry, without the square root, just delta 3. Yeah, that was the point. So, so by doing this, I get a factor with A acting on 0, which is 0. And then the only non-trivial result is with a commutator. And I'm left with the product of two vacuum states, which is normalized to 1. So this is just a commutator. 2 pi cubed delta 3 of momentum. Okay. So, doing this in here, let's say let's see, so I do A2, I commute it past A and then past B. No, wait a minute. No, something is not right in here. What the heck, I'm getting confused. I should get just 2 delta functions, but I seem to get 3 because I commute 1 in here, I get delta 2a, then 1 in here, delta 2b, and then oh no. No, sorry. Let me do this separately. So 0, A1, A2, A dagger A dagger B, 0 is, so one possibility is this is 0, A1, 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 A dagger A, A2, A dagger B, 0, plus 0, A2, A dagger A, times A1, A dagger B, 0. Yes, okay. And then this one is now A1, A dagger B. So I have A2, A dagger A with A1, A dagger B. Okay. But then this term, this first term is now I commute in here, so I get, when this goes here, I give 0. So this is A2, A dagger B, the only non-zero term, and then 0, A1, A dagger A, 0. And this is equal to A1, A dagger A. Alright, so now that works. So, the result is a sum of two products of commutators. So the first commutator is A2, A dagger B with A1, A dagger A. So that's 2 pi the sixth delta 3 P2 minus PB delta 3 P1 minus PA. And then the second term is 2 pi to the 6 delta 3 A2 P2 PA delta 3 P1 PB. Okay? So, and given these deltas, as you see, they equate the initial momenta PA, PB with the final one P1, P2, but there are two different ways. But either way, in the product, this becomes just 2 EA, 2 EB, because EA is equal to one of these and EB is equal to the remaining one. This is 2 EA, 2 EB, and 2 pi 6 is common factor. And then this sum of products, 1 minus EB plus B, 1 minus P2 minus PA. Okay? All right. So the interpretation is obvious, as I said. This thing, what it does is equates the initial and final momenta with the two possibilities that we have. So let's say these are A, B, and these are 1, 2. That's one possibility. And the other one is the cross possibility. Right? So the Feynman diagrams are what we would have expected anyway in the free case. Okay? But the observation that I want to make is that these lines are not connected to each other. So this is not a connected result. Right? So I said in this equality I keep the connected piece. And you see why this happens. Because if I would keep this term, this is part of the one that was explicitly removed from S. I said in here I have just IT, the connected piece. So in here I also must remove this thing. Okay, so removing this term, this zeroth order term from the calculation is obvious. It's not connected because also on the left hand side is not connected. But now let's go on to a more non-trivial term, one with interaction. So let's go to the first order term in this time ordered exponential. So I have time ordered exponential, and from the exponential I can keep just the linear term. So minus I integral minus d to t dt prime h, and well, I can just replace, so the interacting Hamiltonian, we're talking about phi-4 theory, so let's say h prime I is lambda over 4 factorial integral. And here, as before, we have the interaction picture field to the power 4 integrated d3x t. Okay. So together with dt prime, I get d4x, and I forget the integral from minus t to t because it's understood. That's part of what we're doing here. So I'll just write d4x, and then lambda over 4 factorial is a common factor before, and we just have phi-4 in the interaction picture. Be 0. Okay. All right. So we've written this time order product, right? And as I said, part of the Feynman theorem was that there was a normalization factor that canceled, right? So when looking at the connected piece, I needed not worry about that normalization factor. But the next step in our perturbation theory, in the case of Green's function, was, so first we had the Feynman theorem, which was a ratio of two such limits, limit t to infinity or something like this, divided by the part without interaction. But the second part of defining perturbation theory was the Wick theorem, which related this time-ordered product of some field operators in the interaction picture with contractions, with normal ordered product of contractions. So let's say here we have used the Feynman theorem already in some sense, but here I'll use the Wick theorem. Okay, the Wick theorem, which translates this time-ordered product into a normal ordered product, and then I replace this with this plus all possible contractions. Right? That was the Wick theorem. So let's say P1, P2, 0. Now I put normal ordered product, same thing. But when I put the normal order, I have to add all possible contractions. Okay? However, note that when we wrote the Wick theorem for the Green's functions, what we had here was just the vacuum of the free theory. And then this normal order meant I write A dagger A with A dagger to the left and A to the right, which when acting on 0 meant that this gave 0. And the only non-trivial term in this expansion of normal order was the one where I had total contractions, right? So the second step in the Wick theorem was to say that because I have normal ordering and because A on 0 is 0, the only non-zero term in this expansion is the fully contracted term, right? But now we have to revise this because we are not in the vacuum anymore. We're in a state with an A dagger, with two A daggers, right? One for PA, one for PB, the way I wrote them. That means that since I already have here two A daggers, what would be the non-fully contracted piece would give a non-zero result. But another way of thinking about it, which is the one we'll adopt, is that there's a different kind of contraction. So let's say one way would be that non-fully contracted piece gives non-zero result. But another way of saying it is that there is a new contraction. And remember what the contraction was basically the commutator, right? Because when I wrote things in normal order, basically I wrote A dagger as A dagger A plus the commutator. Right? And this I call normal order, and this I call contraction. Right? That's basically what we did. So now the same thing will happen. So in here, you know, we had this commutator, which was a contraction, but the commutator was in the phi part itself. But now there's an A dagger on the in the state, so it would be a contraction with external states. Which means that I consider the A piece in here and I commute it with an A dagger in the external state. Alright, so let's do this more precisely. So, as I said, we're interested in the new contraction, which is a new commutator, and here I have an A dagger, so I have to look at a piece with A from the interaction picture Hamilton. And this, so phi I was written as phi I plus phi I minus. And plus and minus refers to the positive or negative frequency, which means that phi plus has A's and phi minus has A daggers. Right? So therefore, I'm interested in a piece with A, which is phi plus. So phi I plus x. And I want to see what this results when acting on a state with a momentum. So, well, there was an integral, normalization to k. And then I had this relevant factor a k times e by kx. This is a phi plus. And then p, as we said, is square root 2 ep times a dagger p acting on the vacuum. Okay? And now, well, the rest is numbers, and the only relevant thing is this A dagger, which again, I do the same thing, so A dagger acting on 0. This is written as A dagger A plus A dagger commutator acting on 0, but this gives 0. So the result is just the commutator, which is 2 pi q delta 3 of momentum. So the result in here is d3k over 2 pi cubed 1 over square root 2 ek e to the ikx and square root 2 ep. These are the numbers. And now A dagger acting on 0 is just this commutator, which is 2 pi cubed delta 3 of p minus k. Right? And then still the factor 0. Okay? And now we can do this integral over k. When we put p equal to k, these factors cancel, this cancels as well. So this is just e to the I px on 0, right? So we see that we get a new contraction, and of course, as I said, if I have phi minus of x, you know, I don't, so this has an A dagger, and phi minus will have an A dagger, and well, you say, well, I cannot do anything with it, but then this is A dagger, so it's A when acting on the left, right? So if I have phi I in between zeros, right, phi I plus will give me this fact, and then, and then phi I minus will act on this side. So let's say P phi I minus is phi I plus P dagger, right? All right, so that means that from the phi I minus I always act with it on the left, and the phi I plus I act with it on the right. So all in all, I write the contraction of the full phi I, the full interaction picture field, on this state, and denote it like this because this is how I denoted the contraction. And I define this as the result we have here. X times 0, right? And yeah, and then also the dagger. So P0 phi I x is E minus I px 0. Okay. So these are the two new contractions that we have. All right. So now let's consider the term in the S matrix, which was normal order product of phi 4 plus contractions in between the external states, right? So we have now these four terms. I mean, there's an integral minus factorial and integral, but we have this kind of thing. The contraction is a number, so I can put it anywhere. And then the fully contracted term. Okay. So let's see what happens to both of these, to all of these terms. So let's consider first the initial term. So that's the term. That's the only term that mattered for the Green's function. The Green's function, only the fully contracted term mattered, right? So, but now this term be this. But you see what happened. So this term is, well, there's this integral, but other than that, it's still the 0th order term, right? So this term, in terms of Feynman diagrams, is the 0th order term. That's this one, right? Times this thing, which is a vacuum bubble, right? It's a contraction, another contraction, and integrated over the point x, right? So this is clearly not what we want. All right? We wanted only connected and amputated pieces. That's clearly disconnected. So again, this is a term that contributes to the 1. So it's excluded. All right. So that doesn't work. Then let's try this term. Minus I lambda 4 factorial for x. There's a contraction. Well, yeah, actually there's there's 2 ways of doing this, I suppose. No, wait, why 2 ways? Well, no, not 2 ways. Sorry. Not sure why I wrote 2 here. Anyway, there's some factor. Should be 3 times 2, no? I think. Pick one of the phi's, and then I have 3 choices with whom to contract. Oh no, sorry. Six. No. Yeah. I have to choose 2 of the. Yeah, I have to choose 2 out of 4, which is 4 times 0. 6. Yeah. Anyways, doesn't matter because this is anyway. It will still be 0. Will still be irrelevant. But just to have the correct number here. And then we're left with P1, P2, PA, PB. And in the middle, I have 2 phi's. But as you see, the only contribution, non-trivial contribution is when I have phi, when I can make these contractions, right? So when I can have phi plus to the right and phi minus to the left. Okay? And in this case, however, I can have only 1 contraction, and I'm still left, well, either with A or B, doesn't matter, but the point is I'm still left with something like this. Right? I have the contraction, and then I'm still left with something like this. So in terms of Feynman diagrams, what would this be? Well, this one would be a connection, let's say, well, 1 of B. Well, let me write all 4 terms. So there's, from this I can have 2 contractions to the right, and here 2 contractions to the left. So let's write this consistently. So All right, so so the phi's. What do the phi's do? Well, there's one connection, one contraction between two phi's at this point, so that's one loop like this. And then these things also depend on phi, so this connects x with an external line, let's say in this case P1, and here the same x with an external line, in this case PA, right? So this is connecting 1 to x and x to a, and then connecting, making this loop. Okay? And, and in this case I get P1, maybe like P2, PB. I'm left, but the other possibility that I could have both going into the connecting to the other ones, which would mean I connect x to 2 and to b, and then x to itself. So that's this possibility. And then as you can see, the other two possibilities are these ones. Okay? So these are the four terms. The four terms are, again, the free theory, these two possibilities. And then on top of it, I have a choice of putting a loop on each of the two external legs. Okay? So these are still disconnected. So they're also a contribution to the one in S equal 1 plus IT and must be excluded. Right?
Excuse me, Professor. Can you explain again, sorry, why the only contribution when we contract this phi with the states come from phi minus, phi plus? If you have,
well, because if I have, let's see what else I can have. I can have phi plus, right?
yes.
So that's AA, right? But let's say, so this acts on A dagger 0, and here on 0A, right? So yeah, I mean the point is you have to have the same number of A's and A daggers, because otherwise I can commute either to the left or to the right and get 0.
Okay. Nice.
All right. All right. So we've killed the two terms that seem to us most likely to give a non-zero result. So the fully contracted term, which in the case of Green's functions gives the actual result, and this mixed one also gives a 0. I mean, it's excluded, not gives 0. Excuse me. It's excluded by the fact of being disconnected. So we're left with just this
Sorry.
non-connected.
Once again, what about the term phi plus phi minus? Because then we'll have number of A daggers and
yeah, but this is remember, this is normal order, right? So it doesn't.
oh, so
Normal order means if I have phi minus
right.
phi plus, I must.
Oh, so perhaps
Right.
that's why you wrote 2 instead of 6 in front of. I don't know.
Right, maybe. Let's see. No, but the
Just
point is,
because
which of the phi's?
You saw one of these terms.
Yeah, okay, I did myself confused about the number, but so I don't remember in the big theorem the way I counted. But the point is, there are 6 possible terms of this type,
Yeah.
and then if I normal order that, I still get 6. If I first normal ordered and then tick, maybe I get a different result. but no, I don't think so. Anyway, it's irrelevant. The point is this term also doesn't give anything. So the only non-zero term is the one where I keep all the phi's. All right. So the only non-zero term is where I keep all the phi's, and again, I cannot only look at the normal order term. So I write phi minus, phi plus, phi plus. So let me look at this, and then I'll consider the corresponding prefactor. All right, so now we see that we can, in fact, contract everything with the external states, right? And therefore get a result that is non-zero. Okay? So in this case, what do we get? Well, first of all, these are all the same x, right? And so it doesn't matter which contractions I make in here, the result is still e to the I PA, e to the I x, PA plus PB. So e to the I x PA and e to the I x PB from this. And from the dagger I get with a minus sign, minus P1 minus P2. Right? And then 0, 0, which is 1 from the contraction. Okay. So now let's look at the prefactor. So we have minus I lambda 4 factorial, then integral b for x. And now this contraction is P plus Pb minus P1 minus P2. And we are only left with seeing how many terms we have. Well, I look at normal order term of phi 4, and phi 4 is phi plus plus phi minus. And so the only question is how many terms like this do I have? Well, so now I can count really in this. How do I make the contraction? So I can say in here I have 4 phi's, and so I can pick one of them out of 4 to make a contraction with A. Then I can pick one out of 3 to make a contraction with B. Then I can pick one out of 2 to make a contraction with 1, and 1 remaining to make a contraction with B. So that's 4 factorial, right? So 4 factorial cancels, and the integral is 2 pi 4 delta function of the momentum. Okay, so this is really, we recognize this factor, this is just the vertex factor for the phi 4 theory, right? 1, 2, A, B. Okay. So that's good. That means we have gotten what we expected. At first order, we expect the only connected and amputated, whatever that means, we'll see it next. But we expect this the non-zero part to be just the 4 vertex. Okay. Well, one observation is that if I look, so the result was for IT, this was equal to this thing, right? But this was defined to be minus Im times 2 pi 4 delta 4 of momentum. Okay? So if I look at M, well, first of all, sorry, not plus, sorry. So first of all, IT, so the I is present in all of them, in IT, in the result, and in M. And then, moreover, if I look at M, I can also peel off this part. So what I find is that to this order, M is equal to minus lambda. Okay? And then I remember the formula that I derived last time for the differential cross-section d sigma d omega in the center of mass frame was the absolute value of m squared over 64 pi squared center of mass energy squared. So absolute value of m squared now is just lambda squared. So we derived the differential cross-section for a 2-to-2 scattering in 5-4 theory at 3 level. This is the result. And, well, you see, this is independent of angles or anything, it's just a constant. So I can also integrate it. So sigma total then is just this d sigma d omega times the full angle, which is 4 pi, right? So this is just 1 over 8 32 pi. Oh, sorry, yeah, no, it would be 1 over 16 pi e center of mass squared times lambda squared. However, we don't know how to distinguish between, since we're talking about scalars, I mean the cross-section I've calculated is a cross-section for scalar particles which have no identifying characteristic. There's no spin, there's no charge or anything. So there's no way to differentiate experimentally between the final states 1 and 2. So one must divide by 1/2, and the experimentally measured result is 1 over 32 pi e center of mass squared to average. Okay. All right. So we did an example, and in the process we've calculated total cross section for some scattering, but we still haven't touched the point of what is amputation. We've said there's something called amputation, but I haven't defined for you yet what that is. All right. So to do that, let's go to second order perturbation theory and see what amputation is. So we need to exclude something that's not amputated. So in order to see what happens, let's consider, so I will not write all the possible diagrams, but let's consider for amputation, consider the corresponding, the following diagram. 2-point diagram. So this was the first order diagram. And among the second order diagrams is one where I introduce one more vertex in here. And as for remembering the zeroth order piece imply the first order piece where I have a blob on one of the legs, right? The same way now the first order piece implies the second order piece where I have a blob on one of the legs, right? So if this is an x integrated over, this is a y integrated over, so we have a second order perturbation theory corresponding to the two lambdas in this diagram. And let's see what the results of this diagram would be. So let's put some momenta in here. Let's say this is 1 and 2. So this is P1, P2. And this is A and D. This is PA, PB. But then in here, let's call this P prime for the moment. And in here, let's call this K. All right? And the integrals corresponding to the final integral corresponding to this would be an integral over P prime with minus I over P prime squared plus M squared, and an integral over K with minus I over K squared plus M squared. And then from the two vertices, I would have two factors, well, lambda squared if you want, and minus I lambda squared and 1 over 2 from the symmetry factor. But then we would have delta 4 of momenta at the two vertices. So one of them is P1 plus P2 minus PA minus P prime. The other one is 2 pi 4 delta 4. Here K minus K cancels, so we have just P prime minus PB. Right? And so when I do the integrals over, well, let's say the integral over over P prime first. Right? Then I get P prime equal to PB. So I get minus I over P squared plus P prime squared plus M squared at P prime equal to PB. Right? That is to say, minus I over PB squared plus M squared. But PB is external line, right? So that's on shell, obviously. So PB plus squared plus M squared is 0. So this is minus I over 0. Okay? So that's ill-defined. Okay? So, in order to have something well-defined and finite, I mean, this is not just infinite, but always infinite. There's no way to remove this by any renormalization, as we will do for loops, because this has something to do with the external line. So the only thing that we can is just remove this diagram. Okay? So this is removing this diagram is part of what we mean by amputation. We need to amputate in such a way that this diagram is removed. Okay? And you see what the point was, that this appeared because there was this vertex on an external line. There was this blob on an external line. So we have to remove this. If I just cut this here, then suddenly this looks like an external line with nothing on it. So this makes us understand a little bit what amputation is supposed to be. So amputation then is, you look at the diagram and you go furthest, you cut the external piece by going furthest into the diagram until, you know, by cutting it, you just remove something that's not connected in other way, right? So, so you find the furthest point from the external line by which you can remove just the cut just the propagator and then remove the whole piece of the diagram. So, you know, that means that, if I look at this diagram from the point of view of this leg, then I can only cut the propagator in here, right? So if I have something like this, then I just amputate it to this. But if I have something like this, so let me make it a little bit more complicated. So I don't know. Yeah, 5/4 is a little bit hard to do. Well, something like this, and then yeah, here the examples I wrote are kind of complicated, 5 cubed and plus 5/4. But let me just say in 5/4, well, something like this, and then some other block. Then clearly I can go, you know, going on this leg inwards, I can reach here and still cut and remove only one piece and be left with something connected, right? So this is also amputated to something like this. And you see really why this was something that we must do. So by doing this, we remove something that contributes to the 2-point function for the external legs, right? This part that I removed is part of the 2-point function for the external legs, right? So I remove all possible pieces that contain 2-point functions for the external legs. That's the physical interpretation of amputation. All right. So we can say then I can say algebraically that Im times this momentum conservation delta function is the sum of connected and amputated diagrams. But then there's still this factor of square root of z to the n plus 2 that has to do with some loop corrections in the 2-point function. All right. So now let's write finally the Feynman rules for S matrices.
I don't see. We excluded the disconnected diagrams because it's in the S matrix. It's part of the identity, but the amputated diagrams.
Well, as I said, this was part of the normalization constant. So I said the one was related to the connected construction, but even the connected construction itself was not really 100% have to do with just removing the 1. The other part was with writing an equality, whereas previously I had just a proportionality. So the proportionality turning into equality amounts partly to some of these connected issue and partly to the amputation. Okay? That's the correct statement. And in terms of a theorem, well, it's actually the LSZ theorem that does that, which is, I've been building up towards it, and it's actually not a fully completed proof. There's a slightly better proof of it would be quantum field theory too. The actual proof is somewhat long. Anyway, so because of this, I was forced to, because of not having a theorem to be based on, I was forced to do this diagrammatics to just show you what goes wrong. I mean, you understand that when this happens, I cannot get the right result simply because, well, the IM is truly finite, right? And in here I get the same the same delta function which I have on the left hand side, but also get this infinity which is not there. So clearly the equation is not right, and it has to do with the normalization factor. Right? There's an infinity being hidden there. Okay. And now we can see that the infinity was really infinity in this 2-point function. So what I removed here was removing the 2-point function for the external line. All right, so now let's write Feynman diagrams, Feynman rules, for S matrices, which means for M, right? Okay, I can consider also for the identity if I want to. All right, so, well, the first things are kind of obvious. So in X space, I have a propagator, d of x minus y, final propagator, then the vertex, minus I lambda integral d for x, and we've seen the same external line, which comes now from so now the external line has a better interpretation. Some of you were kind of not very happy with the way external line was introduced for Green's functions. Indeed, it was somewhat forced, depending on what you meant by the external line here, whether you put an x on it or not. But now it has a very concrete interpretation that was just a contraction with the external state. So this is now e to the IPX. So let's also remember that this propagator was this, and then the vertex was this, point x. And the external line. Now the external line really means a contraction. Remember, this is amputated, right? So the only thing that I can have here is a vertex. That was part of how I amputated. If I didn't have a vertex, then I could amputate further, right? And the point of amputation was also that in the end I have to have one of these phi's in a vertex, in a lambda phi 4 vertex, contracted with the external line, right? So I have this thing, and there's a momentum coming in, and then this gives us, this gives us e to the IPX. And of course, divide by symmetric factor. Then in P space also I have the propagator dp, df of p is minus I of p squared plus m squared minus I epsilon. There's the, and as before. And then there's the vertex minus I lambda. Okay, and now external line is 1, as before. And we have momentum conservation at vertices. And integral d4p to pi 4 for loop momenta. And divide by symmetry factor. So, okay, so this is somewhat clear. I mean, it's all the same Feynman rules we had before. The only thing that is different, really, is what this applies for. So this applies only for things where we've amputated. So we had an external point, and then we cut it. We write even like this. We don't write anymore a blob on the external line. Right? We just write something without a blob on it. And remember that we did this amputation. So we removed all pieces that were part of two-point functions. And then when I start here, I already have an interaction vertex of the first possible connection. All right, and so once again, to remind ourselves, the LSZ formula is rewritten now as the S matrix element minus the identity, the one that identifies the initial and final states. That is the matrix element of IT is 2 pi 4 delta 4 of momenta times m. Right? And now this is limit when the external lines are on shell. And I can write it perhaps in this form where it becomes obvious that these are external two-point functions. And then G tilde n plus n of pi and kj. And then remains the fact that we've discussed that the factor of z, minus I z. So I've written this way because of the fact that the two-point function on shell, so the pole is minus I z over p squared plus m squared minus I epsilon. So I remove these poles, these on-shell poles, right? But then I remember that this factor of square root of z, this factor of z belongs to two external lines. So in fact, I have to put the square root z to the n plus m to cancel. In fact, in here I would just have square root z. But I've written it this way to emphasize the fact that they have the two-point functions for the external lines in here. Okay. So really, the amputation is dividing by this on-shell limit of the external 2-point functions. All right. So one question, perhaps for you. So I've written here for you the Feynman rules in X space and in P space, but you might notice that this is all Minkowski. So why didn't I write in Euclidean space?
In Euclidean space, you don't have this problem with the on-shell.
Yeah, of course. Yeah, indeed. So as matrices and on-shell states, you don't have Euclidean space. Euclidean space, p squared is positive. So S matrices can only be defined in the Minkowski space because that's where you have evolution and on-shell states. Okay. All right, it's an important thing to remember. Okay, so that's everything I wanted to tell you today. Do you have any questions? All right, so then maybe let's stop the recording.